last of the introductory slides on what kind of processes go on in plasma. There's the electrons and ions, and they're moving around. So there's some random motion, which we catch in the velocity distribution. There are wave processes, electron acoustic or plasma waves. There's electromagnetic wave propagating in the plasma. And there's all different kinds of processes that involves. So this is the one that's describing scattering. Scattering can happen at both the linear level and at the nonlinear level. The linear level means that, for instance, you have a wave, plasma wave, that's existing in your plasma, and you send in a probe, an incident wave. So for instance, this could be a magnetically confined plasma, which for sure has electron and ion acoustic waves, acoustic-like, but with charged particles propagating in the plasma. And you send in a focused laser beam, not focused too tightly because you don't want to perturb the plasma too much, but you send in a laser beam and these two interact. There's a scattering process. It's just like the scattering in a crystal. You're going to get the same equations. And this incident wave scatters off and goes out in some direction depending on the vector components here. So that's where it would look like this was the crystal. This is the light or X-rays coming in, but it could be a light, visible laser or infrared laser scattering off it. And when you look at the equations, the Maxwell's equations with the currents and everything else, you find, as we have before, we did a general scattering diagram in chapter 3, and we found that there was a vector relationship between the K vectors, and there's a relationship among the frequencies. So for instance, this vector relationship here, K incident, is going to wind up being equal to the K vector for the plasma wave and the scattered wave, okay? Or the scattered wave is equal, actually I should have written it the other way. The scattered wave vector is equal to the incident wave plus the plasma wave. I'll change that because this is the outgoing wave, okay? And these are the frequencies. So if this plasma wave were just a crystal, then omega p would be 0. It would just be sitting still, and the scattered frequency would equal the incident frequencies. I'll change the subscripts on this. Okay.
So here, the plasma wave is the wave of electrons?
Yeah, for instance, yes. So there are two acoustic-like waves, plasma waves. One is a very high frequency where only the electrons are oscillating because it's so high a frequency, and the ions are just uniformly providing a uniform background of charge because they're massive. So that would be the electron acoustic wave, we'll call it. There's also a lower frequency wave in which the ions do move and the electrons move also. And that will have a name, has various names, but ion acoustic wave is one of them. So these would be waves that just naturally propagate in the plasma, that just come out of the noise, that just be there in the noise, or you could stimulate them to propagate. And then your incident radiation comes in, microwaves, infrared or visible light, laser or X-rays, and scatters off that, just like the X-rays scattered off a crystal. It goes in some direction. And that would get from this vector relationship. So that's the linear process. The plasma is already there. It's propagating in your magnetically confined plasma. But there is also a nonlinear version where the incoming wave is intense and it's focused down to a relatively small spot size. It's at high intensity is what's important. And this would be like in laser fusion, where they focus, very powerful laser beams are focused onto a plasma to create a plasma so hot that you could potentially reach fusion conditions where you But what happens sometimes, actually has happened quite seriously in this laser fusion situation, what they call inertial confinement fusion now. The incident light, if it's has to be intense because you're trying to heat the plasma to very high temperatures, multi-kilovolt temperatures, so it has to be intense. But it turns out that there are nonlinear processes in the plasma. We'll see them in the equations in a moment, where if this incident light wave is intense enough, even if the plasma wave didn't exist before, it's going to drive it out of the noise. The incident wave is intense enough that if it can satisfy these relationships. If these plasma waves could naturally exist so that these relationships could occur, this incident light can actually drive the plasma wave out of the noise and then scatter off it. And that's called nonlinear scattering. So if you have a linear version, for instance, there would be Thomson scattering. It's a very, very useful tool for diagnosing magnetically confined plasmas, okay? Where the light comes in, the plasma waves already exist, it scatters off them, and you learn about the electron density and temperature, and you even learn about what plasma waves are there. So that would be linear, where this is a modest intensity. A nonlinear one would be like in laser fusion, where you drive the waves out of the noise. Any comment on that? Okay. So the next few slides are just about, well, what tools are there? If you remember, I had this diagram, this one, saying that basically you needed theory. You needed something. What is the functional relationship between the different processes going on? How do they depend on density or temperature or gradient? You need some guiding theory, but the processes are so complicated and they're dependent on density and temperature profile that you really need to use computations. And in fact, if you get into the highly nonlinear theory, or not theory, if you get into conditions in your plasma and your illumination, for instance, where it's so intense that the nonlinearities become very strong, you also need to use computations. And then basically you need experiments. You need all three of these. And so this next few slides is just about the computational tools that people use. So one is particle and cell simulations, where you take a finite number of particles. In this case, it's showing an electron density versus distance away from a surface, let's say. And the electron density is shown as a ramp going up, just going up to the quarter critical over 4. So the light wave could still get through. Again, I'll explain in a moment what we mean, remind you about what is the critical density. Critical density is where the incident light wave, if it gets that far, will be reflected away. It cannot penetrate beyond or into a plasma at the critical density. So this is below that. This is where the incoming light wave could reach all of these densities. And there's a finite number of particles that are simulated. One of the simulations is shown here. It's plotting electron velocity versus distance. And if you look at the simulations here, you'll see where with strong enough and with strong intensity incident radiation, like in here, you start to see plasma waves appearing here, being driven out of the noise. So that would be one of our nonlinear processes. And you can also see in these simulations what is the electron distribution, how many electrons versus electron energy. And so the slope of that would give you the temperature. What is the electron temperature? It's indicated here as cold electrons. It just means electrons versus hot electrons. If there were no nonlinear processes, this curve would just drop down straight. But because of nonlinear processes, you can heat up some of the electrons to much higher temperatures. So let's say this plasma originally had a temperature of 1 keV, but with a very intense illumination, as shown on the left, you produce a tail of very hot electrons. Okay? And these are the ones that in general cause trouble. And there's a variety of processes, which nonlinear processes. One of them is called stimulated Raman scattering, is the name of it, SRS, stimulated Raman scattering. So that's one kind of simulation where you just track a finite number of particles. And it's good for looking at nonlinear processes, but with a finite number of particles. A different kind of simulation is also equally important, and that is it's a zoning process where, for instance, it's shown here that there's a flat disk target, what we call lollipops. And the disk is some material, maybe titanium or silicon or something like that. It's shown as having a diameter and a thickness, and incident laser light is coming in and illuminating an area shown to have a diameter here, half the size of the lollipop. And so here's how a simulation is done. It starts in zones, and this is the profile of the incoming light. So if this is 75 microns, this should have been half of that. And another thing for me to fix. And also, yeah, so anyway, so here's the laser light coming in. And these zones, initially, all of the zones are very compact. And the light comes in and it's partially absorbed near the surface or at the surface at the very beginning, and heats up some of the plasma. Some of the electrons are just, the surface is heated up, and what happens is what's called an ablation process, where some of the electrons and the parent atoms, now ions, come off with them, and they start expanding into the vacuum, which is at a very low density. So the zones, the very fine zones, are expanding as the plasma goes out. There's some material here, but it's at a very low density. That's why the zone has expanded and it's shown to be larger. And at the heating surface, what's called the critical surface, energy is absorbed, so there's some ablation going out, but there's also some energy. The electrons, heated electrons, can now penetrate into the material a little bit. And so there's some heating just behind the critical surface. And for this simulation, these are electron density contours. Contours of constant electron density are shown here. Because the plasma is charged particles flowing out axially, it generates magnetic fields which wrap around the axis. And the critical density we normally plot as N, meaning electron density, critical electron density, in this case over 4. For the simulation people, they typically convert that from electron density to mass density, because these codes, it's just the way they run the codes. So these are two different kinds of simulations which are used, and they're extremely valuable. This is good for understanding particular processes like the stimulated Raman scattering. This is extremely valuable when you're doing experiments, because you may be probing a plasma to find out what's the electron density and temperature, but you have such sharp gradients in density, electron density, and this evolves in time very rapidly. So there's a very important time component. It's very hard to understand your experiments without using these kind of simulation tools. So these go very closely together. So here's just a diagram of what those last two things look like. This is showing electron density at some surface. Again, it could be a solid surface. It could be a small glass sphere. It could be one of those little lollipops of some material. And the laser light comes into and it reaches a surface, the critical surface, where it gets bounced back. whatever light got in at that point may get absorbed there. Hopefully a lot gets absorbed in the region just below, just before that, which is a lower density. But there may be some additional absorption right at the surface, and then whatever's left over gets reflected, because no laser light is going to get past the critical surface here, okay? And behind that, there is a heated, hot, dense region, okay? It's heated by electrons that were produced here and diffuse into the material, okay? And these are some numbers, some typical numbers. The laser fusion studies in general, or in early days, and perhaps even now, use neodymium light at 1 micron. They actually use frequency doubled and frequency tripled, so 1/3 of a micron. And for instance, for neodymium at 1 micron, the critical electron density is 10 to the 11th electrons per centimeter squared. For the tripled light, it goes up as lambda squared, and it'll be almost 10 to the 22, so it'll be up much higher, okay? And these are some electron temperatures that you would have. These would be the sort of background electron temperatures. There could still be some hot component, okay? If your surface density is very sharp to start with, you don't get the advantage of absorption in this lower density region just outside the target. So if it's too sharp, so one of the things that's done is before your main laser pulse comes in, maybe a few nanoseconds in advance, you send in a weaker component of the same light. And that produces a little plasma that then expands into vacuum and fills this region. And it can greatly improve your absorption processes, okay? Because the very sharp profile is not so good for absorption. It all has to happen right at that thin surface, whereas this way you spread it out more. So that's what this comment is about here. With regard to emission of X-rays or VUV, EUV, this is showing some spectral emission intensity versus photon energy. And when the light comes in, go backwards, when the light comes in, it's producing a plasma here, and the plasma is hot enough in these temperatures that it starts to radiate. And that's what this next slide is about. In general, there'll be a strong thermal radiation component, which we'll show later. You need those simulations to do this properly, but we'll in fact find that we could even look at equilibrium black body radiation, which is so simplistic, but in fact actually quite valuable. So there'll be a general thermal distribution of X-rays coming off, depending on what the temperature was, but there'll be emission lines which are associated with the atomic processes going on. So the light's coming in, it's producing electrons at the surface and ions, and the ions can be in a variety of states. So they could have lost one or two electrons, or they can use, depending on the atom and the intensity, maybe lose 10 or 20 electrons. So in fact, this might be an example of where there's K-shell emissions, but they're from ions that are ionized 5 times, 6 times, 7 times. So the K-shell lines, the binding energy shift a little bit. With every electron that's removed, the binding energy of the remaining ones is reduced a little bit. And so you'll get different K-shell emissions, even for the same element, let's say all for silicon. Okay, you'll also have L-shell emissions at lower energy, and it's the same thing. Depending on the different ionization states, you could have a lot of lines. There are times where you don't want a lot of lines, you only want one of them, and I'll show you a trick later, which we call ionization bottleneck, where you N-A-N, ionization bottleneck, where you try to arrange the ionization state in the ions to mostly be in one state, let's say +10, something, and not have these other lines. So sometimes that's important. For instance, for probing plasmas, you might want to just have a single narrow line. You don't want a couple of lines. So we'll come to that later. And depending on whether you have, all your processes are near equilibrium, or if you have some non-linear processes going on, as we discussed a little bit before, you can wind up with a so-called hot tail, or superthermal electrons producing superthermal X-rays. And it is these processes that really dealt the so-called laser fusion a gigantic setback quite a few years ago. This is just what black body radiation looks like. Okay, it has this form where X is h bar omega over kappa T, and the black body radiation has a peak at about 2.8 kappa T. So if kappa T was 100 eV, the peak up here would occur at a photon energy of 280 eV. If kappa T was 100 eV, the peak. So if kappa T was 1,000 eV, then the peak would be almost 3 keV. And the radiated intensity, and it is intensity, is proportional to kappa T to the fourth. So whatever the temperature is, the intensity goes up. So as you increase temperature, this really starts to play a big role. And we'll find that although it's very simple, simplistic or simple, it can be very valuable. This model, a simple model. Okay, so here's a little bit about the continuum and the line emission. Line emission meaning from atomic allowed transitions from radiation resulting from allowed transitions in some ion. So let's start with the continuum. Suppose the plasma has a bunch of electrons racing around in all directions, and there's a bunch of ions there, and they're ionized to some state. So they have, for instance, maybe it would be a silicon atoms that have been ionized. So silicon's 14. Suppose it lost 4 electrons, there'd be a neon-like atom, neon-like ion here, meaning it has 10 electrons. It's a closed shell. But anyway, it's just an example. And then there'd be random electrons coming around in all directions. And here's one coming in, an electron with a certain velocity, and it feels the Coulomb attraction of this heavy ion, charge +4 in this case, and it's pulled towards it this way. So there's an acceleration here. If the acceleration is this way, think about that dipole radiation. If the acceleration is this way, the photons go out this way. Okay, and so that would, if it comes in close, it has a strong acceleration, and it's going to throw off a higher energy photon. Another electron may be coming on the same path, but out further. And by the way, this thing B is called the impact parameter. So maybe there's another electron coming in the same direction, but at a further impact parameter. So it doesn't feel as strong an attraction from the ion, and so it's deflected not as much. The acceleration is not as much. It gives off a somewhat lower energy photon than this one. Okay, and you can imagine that in the plasma, there are all of these possibilities. And that's why you get that continuum radiation we saw before, because you have electrons. First of all, you have electrons of many, many different energies, which alone is going to affect the acceleration, but also all kinds of impact parameters, all distances. So the net result of this is that broad spectrum I showed you before, and that's the thermal part. Okay. Also thermal, but not a continuum, are the bound-bound transitions that you can get. So this is showing some initial atom. Again, let's say it still could be silicon, so Z would be 14. But in this case, what is it saying? This. Let's start with this one. It's got 2, 4, and 5, whoops, and 6, so it's got 10 electrons. So it was a silicon atom, so the nucleus is 14, and it's got 10 electrons, so it's lost 4 electrons, okay? The 4 electrons have been removed by collisions with these other electrons that are flying around, and this is the ion, okay? So this is a case where it's got 10 electrons, so one of them is in the outermost shell, just because it's been excited. So there was not only ionization to remove some electrons, but there's also impacts which would elevate or excite the ion to go from one of the electrons to go from n equals 2 to n equals 3, but eventually going to drop back down and give off a photon that's appropriate for that energy difference, okay? But this is when you've got 10 electrons, this thing could be further heated by impact or further ionized by impact from one of these free electrons coming near this ion, and now there's only 9 electrons. Could still have the same excitation process with the 9 electrons where an electron goes up, but notice that the energy levels have shifted a bit, okay? With the 9 electrons. The nucleus is not shielded as much, so you can see that there's going to be energy level change. So now the photon that's thrown off here is not the same as this one. There's going to be a slight difference, okay? And again, with lesser electrons, same processes, same excitations, ionizations, excitations. The photon energies for this same ion, same nucleus, but with different amounts of electrons still remaining surrounding the nucleus, the photon energies due to these transitions, these n equals 3 to n equals 2 transitions, are going to be slightly different. So I think there's some data here, yeah. So this is from a group at the University of Central Florida, Bill Silfast, who has a great laser book, if any of you have ever seen it, and graduate student at the time, Mark Klausner. And they're looking at here at, they've measured what kind of emission is coming off a xenon plasma. So they were involved in the EUV lithography program, which was looking for photons around 11 or 13 nanometers at the time. Now everything's now settled around 13.5 nanometers. Okay, but you can see the emission lines from xenon with a charge state of +8. That means it's lost 8 electrons, +9, 10, and 11. So here, these emission lines are due to xenon ions, which have lost 11 electrons. Okay, shorter wavelength, higher photon energy. So that's one example. I think there's another one too. Oh no. Oh yeah. So this is about the ionization bottlenecks. So this is in the book, in the plasma chapter, and it's showing different atoms, starting from carbon going down to chromium, excuse me, not chrome. Chrome is on the car, chromium is the atom. But anyway, just looking at argon here, this is the ionization energy required. So for instance, for an argon ion, this is different ionization states, okay? When it says 27 cobalt, what it means, it's like cobalt that has 27 electrons. It's actually, whoops, yeah, going out there. Let's, because we're looking at argon, let me look at the magnesium light. In fact, let me look at neon light. This is neon light, meaning that any of these atoms in this column, this is the energy to remove an electron when the ion has 10 electrons. So this is for argon with 10 electrons. This is the energy required to remove one of those 10 electrons. So the neon is a closed shell. So it's a kind of high energy, 420 something EV, to remove one of those 10 electrons. But for that same argon ion, if it had 11 electrons, sodium-like, okay, it would take only 143 EV to remove that electron. So removing these electrons is relatively easy. 100 and something EV. But after removing the 11th electron, the one electron that's outside of the closed neon shell, that took 143 EV, but it now left you with a neon-like argon atom. So an argon atom with 10 electrons, closed shell, big jump here in EUV. So this is what we call an ionization bottleneck. If you had a temperature of, let's say, 100 EV, the peak is at, let's say not 100 EV, let's say 80 EV temperature. The peak is at 2.8 kappa T, so 240 EV. It'd be easy to remove all of these electrons, and including the 11th electron. If the temperature was just a little bit less than this, you'd easily remove this one. But the 2.8 kappa T wouldn't be enough to remove one of the closed shell electrons. Okay, so there's a big jump here, and you can arrange your electron temperature by the laser intensity that you're illuminating with. You could arrange your temperature to be low enough that you remove most of the 11th electrons, the sodium electrons, but intensity good enough for that, but not enough to remove one of the neon-like. So in this situation, all your emission would be from neon-like ions. You wouldn't have hardly anything from these argon ions with 11 or more electrons, because those electrons would be gone. So yeah, and this is just some examples. 143 EV to remove the 11th electron and form neon-like. This guy's gone here. No further ionization with proper plasma temperature. Don't let it get too high. And then you've got neon-like, and you have a lot of them. And this says that there is strong 3s to 2p and 3d to 2p line emission. And these are the wavelengths and photon energies that you would expect to see from an argon ion. So that's an example. And so anytime you can get a closed shell like neon-like, there's a big jump. You see, from removing the 11th electron, then very hard to remove one of the closed shell electrons. So that's a trick one plays. And so that's for a neon, which is a closed shell, but helium is also a closed shell. So for instance, look at titanium here. We're going to show a slide later. If you can get titanium, where are we? If you can heat it enough so that, for instance, you've gotten to the point where there's only 3 electrons, it's lithium-like titanium, to remove one of those electrons is 1.4 keV. Okay, so you'd have to have a good healthy temperature to get rid of them. But once you do that, now you've produced a closed shell of helium-like, and boy, it's removing another electron is a gigantic jump. So for instance, for probing plasmas, people have used these titanium discs illuminated at high enough intensity to produce an electron temperature of, say, 500 or 700 EV, enough to get rid of all of these, remove the 3rd electron from the titanium. So titanium is 22. So this is like a plus 19 charge state it's got, right? And then over here, you plus 10. Is that right? Plus 12. Okay, and so there's a big jump here. And people use this very successfully to get just titanium atoms, helium-like titanium, and look at the emission from them. So I think I have that slide later. We should stop for a question or a comment, especially from the plasma guys. Okay, so these tables are in the plasma chapter. So what comes next is the development of the equations. What can be done microscopically, kinetic, and fluid. So in the microscopic description, you have the positions and the velocities of every particle. So clearly you can't have too many particles. So this is that particle in cell simulation. This is what they do. Okay, they write these two equations and they apply them in steps to every particle in the simulation, which could be a number of thousands of particles, okay? But this is only done in certain simulations. Then there's the kinetic distribution, the kinetic description, where you describe things, you don't track every particle. In fact, you replace that with a velocity distribution in space and in time, right? So what is the distribution of velocities, that sort of thing that goes over with temperature and may have some hot tail or may not, and how does that vary in space and time? And that's called a kinetic theory, and we're going to have a look at that in a moment. And there's a little bit of, I would say, tough sledding here. The plasma people will probably be familiar with this, but I think for everybody else, going from the microscopic to kinetic, I'm just going to outline this process quickly. I think for those who are interested in this, you have to read the chapter and you can get back to me. And if necessary, those who have a strong interest, we could meet separately. We could have a Zoom meeting to go through some more of that. Anyway, from the kinetic theory, in terms of some velocity distribution function, we can develop the fluid equation. And we talked about this briefly before. The fluid equations for a plasma would be written, the equations would be written in terms of an electron and ion density, how many particles per cubic centimeter, an electron temperature. In some cases, an ion temperature is required, but not so much for us who are interested in high frequency X-rays. And then a pressure and a velocity. An average velocity would be, what's the velocity that the plasma is moving at, slowly and not so slow, moving on average. Besides, the particles will obviously not all be moving at the same average velocity, so there'll be a velocity, an average velocity plus some fluctuations, and we'll deal with that. Anyway, the fluid equations would be conservation of particles, the continuity equation, the conservation of mass, basically. Another equation would be conservation of momentum. This is the forces acting on a fluid. So with that control volume, this could be, for instance, for a neutral, gases or liquids, you would have viscosity, and you would call it the Navier-Stokes equation. Okay, and then a conservation of energy. So you have a lot of unknowns. There's a lot of parameters here, and you have to come up with the equations to describe their evolution. That's what these are, but with enough information to solve the equations. And so we'll do that for a couple of cases. One, we'll look at the expansion of the plasma off a surface. What velocity does the plasma expand from some illuminated, irradiated surface, and how does that depend, for instance, on the electron temperature and other things, okay? So we're going to go through these now, and it may seem a little bit painful. I'll just do an overview, and interested parties should read the book and come back as you wish. And then we'll get into more interesting, some applications of those equations. So the microscopic description is a stochastic function of velocity, space, and time, and it's six-dimensional: velocity, space, plus a time dependence, okay? And we write it, since the particles are so small, in terms of delta functions for each particle I, summed over all the particles, is written as a product of delta functions in velocity space and in configuration space. So for instance, when for some particle I having a position vector r as a function of time is moving around, when this equals r, the coordinate, then the delta function is infinity, and we have to integrate that out. And same thing in the velocity space. So the normalization of this velocity distribution function is to integrate over all space and all velocities, and you should come up with the total number of particles, okay? And this is called a phase space integral. Phase space meaning combination of position and momentum, or in this case, position and velocity. So a phase space, when we speak about it, is normally some combination, a product of space, let's say position and velocity, or position and momentum, okay? And these are shorthand notations. So there's no such thing as a delta of a vector, but it's meant here to be a product, okay? So that for this to go to 0, x, y, and z, or x minus x0, y minus y0, etc., okay? And the same thing for the coordinates. What is dr, this vector dr? It's a shorthand notation for the products, okay? So that's a microscopic description. The only thing you can do with this is simulations, okay? But you can average it and form an average. So this is stochastic, so there'll be some average plus some fluctuations away from that. And if you go through in the chapter, you'll see that this average distribution function, f, satisfies this equation. And this is called the Vlasov equation, Russian Vlasov, and it's called collisionless because there's a 0 over here. There's an approximation made that the high frequencies weren't mattering so much. So this is saying that the velocity distribution function varies as a function of time, and that depends on the forces exerted and gradients in velocity space and gradients in normal space, okay? And you need to combine this with all of the Maxwell's equations, and that makes a complete set. And there are certain problems you can solve with this then. One of them I showed you was the Landau damping of plasma electron acoustic waves being damped because of the gradient of the velocity distribution function in velocity, how it varies with velocity. We'll come back to it again later. But anyway, this is representing the particles, and then you have to add your Maxwell's equations. And that sets what's called the kinetic level of a distribution. If you then take this same equation and you multiply it and integrate by velocity, some vector velocity to some exponent, you'll get the fluid equation. So you could get the fluid equations by looking at those control volumes, which the nuclear, mechanical, and chemical engineers all learn about in their classes on either fluid or transport phenomena. You get the same equations, but you get them from the kinetic equation, and it has a certain attraction to it. Okay, so for instance, if n is 0, this is just 1, you're doing this integration, you get the continuity equation. If you put in n equals 1 here, you get a momentum equation. If you put a 2, so it's v or v squared, you'll get an energy equation out of that. So,
Professor?
Yeah.
Really quick, there was a typo in 8.15 on the previous slide. That should be E plus B cross B, not E cross B cross B.
Oh, okay, thanks. That's the third mistake we found today. What slide is that? 21. Okay, I'll probably correct all these and just repost the slides. Yeah. Oh, by the way, so what Josh was pointing out was this is a plus. This is the Lorentz force, E plus V cross B. So this is our original microscopic velocity distribution function, which has the positions and velocities of all the individual particles, and you sum over all the particles. And if you just take a derivative of that with respect to time, this is what you get. And since, and then you do some integrations and you apply Lorentz forces, and you get this equation, which is called the Klimantovich equation. It's how F, that stochastic quantity, varies with time, okay? So it describes the evolution of a microscopic particle distribution function as a function of time. And so this is it. And you just, so this something sweet about this mathematically. You then go to the kinetic description where you don't look at all of the individual particles. You take that stochastic distribution function and you break it up into an average part, averaged over some volume that makes sense, or some time that makes sense. And so there's an average and a fluctuation, the stochastic part that was left in here. So there's an average, and the difference from the average is shown here. And you need to do that with all of the quantities in the Maxwell's equations, et cetera. And when you do that, and you go through the same process, similar process, you wind up with a similar equation to the Klimantovich, which was for every single particle. You wind up with the Vlasov equation. And all of the steps are shown in the chapter. But this is what I showed you before. There's a term on the right, which is a nonlinear term. It's a product of fluctuations, and F tilde is multiplied by a B and F tilde by an E. So this is a product of fluctuation quantities, and often you can argue that the product of the fluctuations is not large, and you drop this, and you also drop it because you don't know what to do with it. It's a collision, called a collision term, but it's mathematically makes life really tough. But in fact, it's reasonable to approximate it in many cases. And if this is zero, what's left here was what I showed you a few slides ago called the Vlasov equation for the kinetic, for the slow varying kinetic version of the velocity distribution function. So for instance, in that case, again, you call that the collisionless Vlasov equation, and you combine that with Maxwell's equations. And now there are certain problems that you can solve with this, which involve more details than you could see in the fluid equations. And this is one that we talked about, was the Landau damping, or in fact, Landau growth. So Landau damping, we just went over this, but you have some velocity distribution function with some characteristic spread to it, which is related to temperature. And there happens to be a wave in the plasma. So the wave is moving along at some phase velocity. So this would be an example of a plasma wave. And this specifically here, this is an electron acoustic plasma wave. So we just call it the electron acoustic wave. And it's shown here. There's understood here to be a uniform distribution of ions for charge neutrality, but the electrons are not uniformly distributed. There's a wave here that has an amplitude shown by the heavy black line, and in this region there's a little bit less of an electron density, and in these two regions near the crest are an excess of electrons. And that's in the presence of a number of electrons just flying around, okay? There's a lot of, let's say, maybe these background electrons here are this group here, but there's some other electrons which are moving so fast that they're not within the potential of this wave, and they're flying, if they happen to be aligned right, flying along. So this is showing what happens when a situation like this is the phase velocity, this is the phase velocity. This is showing that there could be some electrons out in this region, so they're kind of high velocity. And this is showing that because of the slope here, there's a few more electrons on the low energy side, shown here, and a little less electrons just on the high side of the phase velocity. So that's just because of the slope, F prime of V, okay? And so if there are more slow ones, then the potential curve of the wave that's propagating is actually pushing these electrons and therefore losing energy to those electrons, okay? And the electrons that were on the high side over here, they're moving a little faster than the phase velocity, so they're pushing on the net potential of the wave. And so they're giving energy to the wave. But because there's less on the high side and more on the low side, this is going to wind up with a transfer of energy from the wave to the slower electrons, and the wave is going to damp. Okay. What can happen, people have done experiments, is you take this same plasma, but you inject an electron beam. You inject an electron beam with a velocity that's just a little bit higher than the phase velocity. And so you artificially produce more electrons with a little higher energy, and there's more of them pushing on the wave. So now there's going to be an energy transfer from these injected electrons to the wave, and the wave is going to grow. And they call that Landau growth. And I said that there were problems you could solve with all these equations. One of them is, what is the frequency of this wave? You know, there's a dispersion relationship, but you can take the frequency, you remember, the frequency of the wave, okay? And you can write it as a real part plus an imaginary part. The imaginary part gives you either the decay of the wave amplitude or the amplification, where the wave starts to get higher in amplitude, okay? And this imaginary part has this solution to it. Depends on the plasma frequency squared, the electron plasma frequency, the real part of the frequency, k squared, which has to do with the period, the wavelength, okay? And the partial of f with respect to v. So it depends on the gradient just right here. It depends on how many electrons are there. That's this thing. This will give us a measure of how many electrons, which matters. But there's also this gradient of f in velocity space. So this is telling us, are there more slow ones or fast ones? So depending on the sign, if this is negative or positive, you'll either get wave decay or wave growth. That's what this is about.
Professor?
Yeah.
When you say this is a kinetic effect, that means that you can't describe this behavior if you're just using the fluid equations. Like, you need to be at that one level deeper.
Mm-hmm, exactly. Because on the fluid level, you had the electron densities and ion densities, and you had just a temperature. But here you have much more than a temperature. This is a kind of temperature related, but you have all this information about the velocity distribution, which you need to know, and it's just not in the fluid equations. There is a velocity in the fluid equations, but it's that average velocity.
Got it. And so it's the distribution that leads to you understanding these velocity variations and therefore the growth. Okay.
Right, correct. Okay, so how do you get the fluid equations in this particular method? You take the kinetic equation, the Vlasov equation, and you look at velocity to the 0, velocity to the 1 as a vector, velocity 2 as a scalar. You can do other things, and you integrate these things, and you will, if you go through all the math, and it's in the chapter, you'll find that this one gives you the so-called conservation of mass or continuity equation. And the second one is a momentum equation. And the momentum equation looks like this. And for a plasma, an electron plasma where the ions are not doing much, they're just massive, and the frequencies are so high they're not relative moving around. This is what you get. And this is a conservation of momentum, okay, equation. And it's very similar, it looks very similar to the equation for a gas or a liquid, where you would have not a Lorentz term, but you'd have a viscosity term, okay, maybe something else. So that's the similarity there. And again, you have to combine them with Maxwell's equations, okay? And in these things, the electron density here came from this term. It's the integration of the velocity distribution over all velocities. So you're integrating out the velocity component, and all that's left is the space-time, and it's normalized to the electron density, okay? And this V dot F term appears in there. And you'll see pressure. This is a pressure dyadic, where it's a product of fluctuation terms, which is pressure, but this could be a scalar. So it could be that that the velocity can be represented as a scalar, and then you've got pressure as a VV term. So you can see it's an energy per unit volume. Okay, so those are things that go in it, and from this you'll get the fluid equations. This is just showing some detail about how you do it, and this again, how you do it for the momentum equation. So you wind up having to deal with all of these product terms, right? The average of VV, this is the actual velocity, and you represent the velocity as an average plus a fluctuation therefrom, and you go through and you get things like these dyadics, pressure dyadics. So if you're in a situation where the pressure is reasonably scalar, isotropic, then you get this conservation of momentum equation, we call it, okay? Yeah, so it's essentially an F equals MA for a fluid volume of plasma. And this operator we sometimes write as the substantial operator, ddt, cap ddt, right? So I guess a lot of you are familiar with that. And if you go through this thing, you get an energy equation, but it's painful. In the end, you have to make some approximations here. And one is to make a scalar pressure, okay? And if you follow things through, you can obtain the perfect gas law, okay? And the adiabatic condition, and these are going to replace our energy equation. Okay, so for our fluid level plasma, these are our two fluid equations, conservation of particles and conservation of momentum. These equations go with it, Maxwell's equations, and you solve different problems on a fluid scale, okay? So where are we on time? Okay, so this is an example of how do we use those equations to find the properties of an electron acoustic wave, a wave in which the motion involves the electrons propagating, sort of as we saw in those last few slides, okay? It's called electron acoustic. It's going to be at a very high frequency, and the ions are going to be massive and static and stationary, okay? So these are the equations that we had before, and the only thing we need from Maxwell's equations is this, it turns out, okay? And we're going to take the electron density, we're going to do an expansion. We're going to linearize these equations because they have nonlinear terms. They have an electron density times a velocity, so that's a nonlinear term. Here's another nonlinear term. And here you're going to have nonlinear terms also. So to linearize it, we're going to say that the electron density has a background density N0, or drop the E, plus some fluctuation. And the fluctuation is going to be small compared to N0. That's the linearization process. And the velocity is going to be broken up the same way, but we don't want our velocity, we don't need our velocity to be moving on some trajectory. So we're leaving off the zero level velocity. It's just going to be the fluctuation part. And then E and H and everything else would have a background electric field that went with the background density and some fluctuation, okay? And if we make these substitutions into these equations, then the continuity equation looks like this, and that's this one. And the momentum equation looks like this, where we've made some substitutions, okay? And this, and the nonlinear terms have all been neglected. We're just looking for small amplitude waves that naturally propagate in the plasma. And so these three equations can be combined, and this is, we're not going to show you, but taking those equations, and in one case, the divergence of the equation, and the other one, the partial with respect to time, and then combine all of these equations. And so we're combining, we've linearized these equations, and we're bringing them together into this equation. So it's saying it's a wave equation. actually. It's a partial respect to t, the partial square with respect to t of the electron density, some parameters that came from all this stuff here times the electron density, and minus this thing, again, with the gradient squared. So the gradient squared is coming in here. So this is looking like a wave equation. This is a partial respect to, the operator here has a partial respect to time, and it has a gradient squared, so it could be one-dimensional. So you'll recognize this as a wave equation, and these quantities that come up here, this is, remember, this is background electron density. This equation recognizes a wave equation for electron density fluctuations. Remember, this is the fluctuating part. I just left off the wiggle at the top because we don't need to carry it forever. And this is the operator for this wave equation. And this term here is the plasma frequency, E squared n, the background electron density over epsilon 0. That's omega p squared. And these terms here, this is a measure of an electron sound speed, which depends on the electron temperature and the electron mass, okay? So these things are here. So these things are identified. And let me just see. And so we have a wave equation, and we can assume our usual approach is to say, okay, let's let the electron density be some background value times e to the minus I omega t minus k dot r, and see what kind of wave, what kind of dispersion relationship that results in. What does that tell us about the relationship between omega and k? And that's probably what's on the next, yeah. So here's a repeat of that wave equation. Here's the assumed electron density. As we did in chapter 2, the partial with respect to time would be bring down a minus I omega, okay? And the gradient and ik. And so this wave equation now takes this form, okay? Where being equal to 0 for finite n, we want a wave that has some oscillating electron density here. This thing has to be 0, okay? For this to be finite, natural mode, no excitation, no forcing function on our wave equation, this has to be 0, so solving for omega squared, this is what we get. And this is called the dispersion relationship. Dispersion meaning that it's the relationship between the frequency and the wave number or wavelength. So if there was no dispersion, all waves would propagate with the same speed, the same phase velocity. But because of this plasma frequency being in here, the dispersion relationship is going to have dispersion. There's going to be a difference in phase velocity of waves of different frequencies. Different frequencies won't just depend on k, they'll depend on this other thing, okay? And how are we on time? So for this, so this is the dispersion relation, and this is a so-called dispersion diagram where you plot frequency versus k. So you would do the same thing for solid state plasmas, okay? You'd label them slightly differently, but it's going to be the same kind of thing. You get a dispersion relationship and a dispersion diagram. And this is showing the waves that occur in a plasma, simple plasma, no magnetic field. There is our electron acoustic wave, which we've just been analyzing. There's a low frequency ion acoustic wave, which is a much, much lower frequency, shown by the heavy black line. And there's the transverse electromagnetic wave that we spoke about briefly, and we're going to talk about again. So this is a plot, this heavy black line is a plot of this thing. And so the natural frequency for acoustic waves, plasma waves, is at the plasma frequency. And this is relatively flat for a long, long distance in wave numbers. So there's just this natural oscillation at the plasma frequency, the so-called plasma frequency, which was here, okay? So this is, if you have a plasma without any excitation, you are going to have waves propagating in all directions. They may be hardly out of the noise, but they're going to mostly be at the plasma frequency, okay? And it has an important role also for the electromagnetic wave, because the electromagnetic wave can propagate in the plasma at high frequencies. But if the frequency of the electromagnetic wave is going at lower frequencies, this solid line says all of a sudden you get to plasma frequency, it cannot go below that in the plasma. So low frequency waves will not get through. Okay. So for instance, if you're shining a laser into a plasma, if it can propagate at densities, at frequencies high enough that the frequency is greater than omega p. Okay, but if you try to shine your laser pulse, let's say your Ti-sapphire laser pulse, onto a solid target of titanium, it's not going to go into the titanium. The electron density in the titanium is too high. It's 10 to the 24th or something like that, not 10 to the 21 or 10 to the 22. So in a titanium thin film, the plasma frequency is going to be very high, way up here, and the wave won't be able to propagate. Your Ti-sapphire will reflect off the surface of the titanium. Okay, so this is our plasma wave. So the next one to do, so this is, I'm sorry, this is the one we just did. When we come back next time, we'll do the electromagnetic wave. We touched on that at the end of the high harmonic lecture, and there was an error in there that we caught and corrected it both in the upcoming slide. But anyway, this is one of the waves, and we'll look at the electromagnetic wave also. I don't recall if I'm going to look at the ion acoustic wave, okay, which is really low frequency. A good time for a question or comment. For whom is this material familiar or close to familiar? Not a quantum.
I've seen it a couple times.
So have I.
I'm sorry, Josh, you got muddled there. The voice didn't come through.
Yeah, Rob and I have both seen this before.
Okay, you have, great. Okay, so the next one is the transverse waves, the electron density. This is the one that we did touch upon briefly, but we're sort of at the end of the class. So let's start with this next time. Let me just flip through to see what's ahead for us. Well, the combination to get the propagation of the electromagnetic wave, which was this thing. And by the way, I didn't correct this. I didn't bother reposting the slides, but this N should have been N sub E. So back in the high harmonic chapter, at the end of the slides, this slide was also there. And so this needs to be corrected. So we'll do the transverse wave, and then we'll do this, what happens when the electron density in the plasma is too high and the wave can't get in, and we come to what's called the critical electron density and what goes on there. So that's what we'll do at the next class. Okay, and have a look at at my proposed schedule, and any comments are most welcome. And see you Thursday.